Test. Can you hear me? Can you hear me now? If you can hear me, stay tuned for just 1 minute as we take care of a few last-minute technical details. And we'll begin as soon as we get those sorted.
Okay, well, I think everything is okay. So whenever you're ready.
Audio is good?
Yep.
All right. Hi, everybody. Thank you for coming. This is the third installment of the DR Vision Voxel Series webinar. Today, we're going to be talking about neuron analysis. So let's jump in with a brief introduction. Again, this is our series for scientists with beginning or maybe even intermediate image analysis skills who are looking to improve and who want to take a practical approach. So this is not going to be a math-intensive theory-first course, but we are going to be using some real fluorescent microscopy data in some applications that we have worked on at DR Vision here. I'm going to talk a little bit about our company, why we are doing this and who we are. And then, of course, we'll get into the meat of the presentation with a 2D neurite outgrowth example. We'll talk about the recipe and the various parameters, and we'll give you a demo on how that actually works in our software. And then we'll move on to a really cool 3D neuron analysis application. We'll talk about those recipes and parameters and give you a demonstration on how to do that both with automated approaches and with a manual approach. And then we'll wrap it up, and if you have questions throughout this process, you can reach us at Twitter at drvisiontech, on our LinkedIn, our website. Our website even has a forum, or you can reach out to us in the comments here on YouTube. I have our scientific liaison, Quinn, here with me today. She's moderating all of that, and she'll pass on any questions that you have. So feel free to ask away. I would also recommend that you try our 14-day free trial of Aivia. Just get a grip with what everything we're looking at here today, and go to our website, request a download, and try all of the great applications that we have built into that software.
Lily, we can't hear you right now.
Can't hear me. Okay. Can't hear me at all. Can we hear me now? Test 1, 2.
Not 100% sure. He cannot hear you.
He cannot hear me. Okay. At all, right?
At all.
All right. So I turned the video off for right now. This is, come up here. There we go. These are both on.
Yeah.
Here's video.
Could you try turning the sound on and off? We can hear you now.
We can hear me. All right. Sorry about that little snafu there. We're back online. This is the third installment of our DR Vision Voxel webinar series, and today we're going to talk about neuron analysis. So we'll jump in with a brief introduction. Again, this is our series for scientists with beginning image analysis skills, or maybe even intermediate image analysis skills, who are looking to improve. And we're going to take a practical approach using real fluorescent microscopy data and some real applications that we've worked on here at DR Vision. This is not a math-intensive theory-first course. There are some great resources out there, and if that's the thing that interests you, I do recommend you check those out. But this will be focused on some of our actual recipes and their parameters. We're going to talk a little bit about who we are as a company and what we've done. And then we'll, of course, get into the meat of the presentation with a Neurite Outgrowth 2D application. We'll talk about the recipe, the parameters, and give you a brief demo of how that works. And then we'll take a look at a really cool 3D neuron analysis recipe. We'll talk about those parameters and give you a demonstration how to do that both with the automated recipe approach and with a manual approach as well. And then we'll wrap it up and answer any questions you have. Speaking of questions, you can reach us at a multitude of ways. We have our Twitter at drvisiontech, our LinkedIn, our website, and a forum on our website, all of which you can post questions to, or just post a question right here in the YouTube chat. I have our scientific liaison, Quinn, here with me today. She's moderating all of that, and she'll be sure to pass on any questions that you have. You can also check out some of the results from our software at Sketchfab. So go to sketchfab.com/avia/models and see all of the wonderful images that you can get using our software. If you'd like to try some on your own, you can try it with our 14-day free trial of Aivia. Just go to our website and request a download, and I'm sure you'll be impressed. I would be remiss if I didn't give a big thank you to the whole Aivia team. Tuan is our software manager. He works with Bryce, John, and Casey, as well as Michael on the testing side to develop this awesome software. She runs the algorithms group with Hideki, Tsuyen, and Mike, and they make all of these really cool algorithms possible. I'm here with the marketing and sales team, Quinn, Hoyen, and of course our VP of Marketing Sales, Luciano. And I would be remiss if I didn't also thank Chris and Sean, who I don't have pictures for. Our company has been together for over 25 years now. We've been working to improve healthcare and enable scientific advancement. The core group of executives started in 1989, founding a company called Neopath. They developed the first FDA-approved automated pap smear device, and there are even some still in use today, you can see right here. After that company was sold, the same core group founded a new company called S-Vision. In 2008, we rebranded as DR Vision Technologies with a little investment money from Nikon. In this 25 years plus of history, we've developed a wide range of applications. Everything from X-ray inspection and crack detection to some of the really cool biological applications that we've been talking about in this Voxel series, such as cell detection and tracking, and things we'll look at today like 3D spine analysis. We didn't do this on our own. We've had a lot of wonderful collaborators and sponsors, and you can see just a few of them here. They come from all over the globe, but right now they're mostly focused in the US and Japan. We really like working with collaborators. It helps us advance scientific agendas and push the best possible science out there. During this process, we develop some of the best algorithms and software applications, while our collaborators supply us with things like biological images and fluorescent data sets that we can use to develop these algorithms. During this process, we've developed a number of core technologies and competencies. We've got a plethora of patents, especially in the areas of machine learning. Check out some of our other webinar presentations on the very cool machine learning applications that are built into Aivia. So again, DR Vision, that's us. We've recently launched an image analysis as a service platform. So we have in our offices the best software, the best hardware, the best development team, and the best image analysts, that are available on the market. It's a scalable, cost-efficient solution for any of your image analysis needs that doesn't require you to sit in front of the computer for the many hours that it can take. Of course, we also develop our own software. Aivia has so many cool applications, 2D and time-lapse support, as well as 3D, VR, and 15 plus recipe applications designed for specific image analysis tasks. And of course, we also do a lot of contract software development. That's in anything from life sciences to industrial metrology and quality control. So now on to the part that I'm sure you all wanted to come for, the analysis section. So in this process, we have a general image analysis pipeline. There are so many different ways to process images. There are multiple processes that can get you to the exact same result, and there are even multiple valid approaches that will measure different things but get you the analysis or kinds of results that you're looking for. Today, we're going to talk about a process that is built into Aivia. We make it simple yet powerful. There are other ways, and many of the techniques that we discuss in this presentation can be used elsewhere. But I am going to walk through the important parts of Aivia just so that we can all be on the same page. So one general image analysis pipeline that you can keep your eye out for in this presentation looks as such. First, we want to flatten the background. We want to do things like remove noise and enhance edges. Then we want to detect or segment the important parts of the image. So we're going to filter out small objects and debris, and this will include things like dendrite tracing algorithms as well. Next, after we have segmented the important parts of the image, we want to partition them or separate into the appropriate separate objects. This involves things like intensity or contrast thresholds, as well as separation factors for the algorithms that are used. And lastly, once you have these well-partitioned and detected objects, we want to measure. So these are the final results that you'll often get, and they let you objectively quantify the image analysis process. So here's what Aivia looks like. I'm going to give you a brief tour of the UI. You can see, if you've tuned in before, that we have this really cool new dark scheme going. Up at the top, we have a file menu and view controls. So this lets you interact with all of the basic functions that you would expect from software, such as loading, saving, and exporting any image data sets. The view controls manipulate how you actually view data in the software. You can control things like the zoom level or the visualization mode, switching between 2D, 3D, or even VR representations. The main section that we're frequently concerned with is the image panel. This is where you will see any fields of view, objects, or masks that are created in the image analysis process. On the right side, we have a series of side panels. They let you select and modify channels if you have multiple channels in your images. They'll let you select and modify any objects and object masks that are created as part of an analysis process. They let you apply image analysis recipes using the recipe console, and you can even view information in a handy chart format. Next, we have the Contents panel. This has an image explorer, which allows you to open, view, and switch between any loaded image datasets. Annotation tools that let you draw and take measurements on the images. The ability to edit any tracks and masks that are created by recipes. And a spreadsheet that contains all of those important measurements of the datasets. Now, I've mentioned the word recipe a number of times and talked about the recipe console. In Aivia, a recipe is just a series of individual image analysis computations that are done in a sequence to get a specific type of result. So we're going to work with the recipe console today, and just so we're all on the same page, there are several main areas. At the top is a recipe selection tool for loading, editing, deleting, and saving any of your custom recipes. Below that, we have the input and output section to work with multiple channels on your images. Below that is the area for recipe parameters. These are grouped into helpful presets with values that we have found work extremely well. And lastly is the recipe application, so that you can preview and then finally apply the recipe to your image data sets. All right, so let's talk a little bit about neurons. In Aivia, there are three main components. In biology, there are a lot of different components, but we're just concerned with the main structural components right here. The first is the soma, or the cell body. This is what contains the nucleus. After that, these long, spindly things are called neurites, or you might have heard them called neuronal processes. This is any part of the cell that projects or proceeds away from the soma. The neurite is a general term for a dendrite or an axon. It's especially used in cell culture or before differentiation, where these two dendrites and axons can be kind of difficult to distinguish. And lastly are spines. These are small membrane protrusions that come off of a neurite. They typically receive input from a single axon at a synapse, and they're a rich area of study. This image on the left doesn't show any spines, but we do have some that we'll look at more closely when we get to the 3D neuron analysis recipe. So we're going to look at neurite outgrowth detection parameters now. If you've tuned in before, these parameters might look similar to our cell detection parameters. We're going to go over what these do. The background removal factor tells the software how aggressively to remove background noise. A contrast threshold is the minimum amount of contrast needed to detect the edges of an object. The fill hole size allows the recipe to fill in holes in the mask that is created. And a smoothing factor removes fluctuations in the perimeter of the soma. So let's take a look. The background removal factor is important. As you can see here, this image on the left has a very high background intensity and a lot of noise. When we've applied a background removal factor, or background removal algorithm, we can see the results on the right. These results show the cells clearly maintaining some intensity, while the background itself is flat and almost completely black. Contrast threshold is best illustrated by looking at a line intensity profile like this. So I've started with this image on the left, which has a line drawn across a cell body. On the right, you can see the intensity profile starting at 0 in the black background and going up to over 2500 at the fluorescent peak. As we adjust the contrast threshold, illustrated by this red line, we can see the difference between how much of the cell body is detected. With a higher threshold, only the brightest objects are detected. A smoothing factor, as we said, removes fluctuations in the perimeter. On the left, this is the same object as on the right, but with a much lower smoothing factor. The right side, with a higher smoothing factor, doesn't have these little fluctuations in the perimeter. Once we have detected the appropriate soma, we want to filter them based primarily on the size. The object size allows the user to select the smallest and largest sizes of desired objects. Anything smaller will be excluded, and anything larger will also be excluded. A separation factor tells the software how aggressively to separate objects. This is especially important if objects are grouped closely together. Let's take a look. For the object size, on the left we can see that this object is not segmented, although it clearly looks like something that should have been detected. Turns out this is just under our minimum size threshold. So once we have adjusted the size threshold, the object is now detected appropriately, as you can see on the right. Here's some of the results of good and bad partitioning. On the left-hand side, we see some cells that are closely grouped together. It could be easy for a software algorithm to detect this as one group. There's clearly some fluorescent intensity connecting all of the pieces. However, the separation factor has appropriately been applied and separated all of these objects as we would expect. However, if you partition or separate too aggressively, you might end up with something like this right image. See here, we have one single cell that looks like it's been split into two different pieces. So finding the appropriate separation factor is an important step, especially when cells are bunched closely together. And lastly, we are going to deal with neurites. Again, these are the dendrites or axons. A branch sensitivity factor specifies the sensitivity of the branch detection algorithm. Increasing this value enhances short branch detection on a neurite. The mean neurite width enhances the signal of neurites of the specified width by suppressing the background that surrounds that neurite signal. The minimum neurite length is an exclusionary criterion, so any neurites smaller than this length will not be included in the detection results. Here we can see an example of how branch sensitivity is important. Again, this is the same image. On the left, we see this missing neurite. It's fairly dim, so if we increase our branch sensitivity and adjust the mean neurite width, we can appropriately detect this neurite, as we see on the right. Once you've done all of the appropriate processing and selected the correct parameters, you can check out all of the measurements that are taken from your dendrite and neurite recipe and look at them in a spreadsheet. The Soma tab has measurements such as soma area and total neurite length, but we also have measurements for each individual neurite detection object. These measurements include things like the number of endpoints and the number of branch points on each neurite. So let's take a look at how this works in practice. I'm going to pull up our software now. All right, here we are. Here's this neurite image that we've looked at before. I've pulled up our neurite outgrowth recipe. Let's take a look at some of the previews. So each detection or each preset group in this recipe has a preset detection. We can turn that on by clicking the little magnifying glass. Looking at the detection preset, low and medium don't really detect anything, but high looks pretty good. For the subset filtering, small, medium, large doesn't seem to help too much. Let's keep it small for now. And lastly, we have the neurite detection. Low, medium, high. Of those, low seems to look the best, but again, we're missing this section right up here. So we'll take a look to adjust the parameters. I've already done some measurements, so I can tell you that the branch sensitivity looks really good at 54, and the mean neurite width should be increased to 2.6. We can now preview this whole process, and we see that this is correctly detected. Let's apply this recipe. That's it, real easy. You can now see we've correctly traced all of these neurites. We can take a look at the measurements that we've generated again in our spreadsheet tab. Here we see object 1 is our soma. It's got line length, the soma area, and the average intensity. If we go over to this object dropdown, we can also select the neurite mask. Here we see the multiple neurite objects that we have detected including measurements like the total line length, the number of endpoints, and the branch points. It's just that easy in Aivia. All right, now we'll dig into some 3D neuron analysis. On the left, you see a 3D fluorescent data set of a single neuron, and on the right is our reconstruction of that using the 3D neuron analysis recipe in Aivia. Looks pretty good, doesn't it? Let's talk about some of the factors here. The first step is soma detection. Soma diameter is the expected size of the somas in the image. Soma outside this range will be excluded. You can see our annotation on this image here measuring the diameter. Soma partitioning is for the case where you have multiple soma. This can be enabled to separate individual cells from each other. The minimum intensity threshold that is activated when you enable the soma partitioning is the minimum soma intensity, which is used by the watershed algorithm to partition these. The important part here, another important part here, is dendrite detection. Some of these are pretty straightforward. Dendrite diameter is the average diameter of the dendrites you wish to detect, and the minimum branch length is again an exclusionary criteria such that any branches smaller than that will not be included in your detection. The intensity threshold is the range of intensities that are considered by this algorithm. Anything below the low value will be excluded, and anything above the upper value is automatically detected as potentially a dendrite. The mean intensity offset is the value that operates in between these two thresholds. This is used for calculations by the voxel scooping algorithm in order to determine which voxels belong to a dendrite and which don't. We have another switch here that allows us to skip soma detection. Sometimes you'll have an image with a ton of dendrites, but none of the soma that the dendrites belong to are in that image. In that case, we have a parameter for the maximum connection distance, which is the upper limit for how far the software will search to join disparate dendrite segments. And lastly, I promised we'd talk about spine detection, so here it is. We can enable spine detection, or if you're not concerned with them, you can disable them to save a little bit of time in the analysis process. The spine head diameter is the average diameter of the spine heads. The spine head volume is again an exclusionary criterion. Because not all spine heads will be perfectly round, you can exclude objects that are too small or objects that are too large. And lastly, we have the spine neck length. This is the maximum distance from the spine head to the dendrite. So let's take a look at how we would do this in Aivia. I've already loaded our 3D data set here. So let's select our 3D neuron analysis recipe. I've already taken some of these measurements because in a 3D reconstruction, it can be fairly time consuming to make these accurately. I just want to show you how well this works. So we're going to set the dendrite diameter to 10, the minimum branch length to 50. Our intensity threshold will range from 10 to 50, and our mean intensity offset will be set to 2. Let's take a look at the spines in this image as well. Some good values here are 3 pixels and a range from 5 to 400. We'll keep the maximum spine neck length set to 10. We'll click Apply from Beginning, and this will only take about 65 seconds, so just hang tight for a second. Quinn, do we have any questions we can answer while we're here?
Yes, so a question came in for the analysis that you're doing here. The images only have one neuron. Is Aivia capable of doing images with multiple neurons, and is the analysis process going to be different if it's multiple neurons?
Aivia absolutely is capable of handling multiple neurons, both in 2D and in 3D. The process is more or less the same, but this is where you want to enable something like our soma partitioning. So soma partitioning will allow you to separate multiple soma in 3 dimensions. And we already discussed the separation factor for the 2D Neurite outgrowth recipe. So all of these are totally possible in Aivia, and very minor adjustments to which settings you're working with. So yeah, totally doable. As you can see here, we now have our 3D reconstruction. Looks pretty good, doesn't it? We can select individual parts to learn more about them. So here we have our soma, we have dendrites. Let's take a look at some of these spines that we have detected. Each of these spines can be selected, and you see they each attach directly to our dendrite. All right, so that's how you do that process with the automated 3D recipe. It's fast and powerful, and as we just discussed, you can do it with multiple soma and multiple dendrites, or even with no soma. All right, so we talked about the 3D neuron analysis automated, but we do also have some really cool, really powerful manual editing tools. Let's talk about those. First, we have a dendrite pencil. It's got a parameter for the dendrite radius, which we've talked about before as related to the dendrite diameter. And the enhanced trace allows the process to adjust the width of the dendrite to correspond to the actual fluorescent voxels as you go along. We have a connection tool, which allows you to connect different dendrite segments. You can, of course, delete any mistakes or just try again to get even better results. And we can also add spines and soma manually. The spine search range allows the user to specify how far away a spine is from a dendrite, similar to our spine neck length. The soma search range allows the user to specify the size of the soma, similar to that soma diameter that we talked about before as well. So we'll do one more demonstration, this time using the manual tracing tools. All right. Here we have our 3D image. We're going to go over to the Neuron Editing Suite here. Let's begin by adding a soma. Now, I know from before that we look pretty good here using about 52 for our search range. All we do is click right in the area we want to analyze and click Create Soma. And here we have it. Let's try tracing one of these dendrites. We know the dendrite diameter from before was set to 10, so a good radius should be 5. Let's zoom in and trace this section right here. All we do is click and drag, and our software will automatically trace out these dendrite groups. If you can't make it all the way to the end, just start tracing again. and then we'll use the connection tool. Connect point A to point B, and here we have a single connected dendrite. But what about all these spines? Spine search range set to 10. That's again our maximum spine neck length. And we just click on any of these individual spines to automatically generate and connect them. So here you can see pretty closely the fluorescent overlay with the underlying 3D reconstruction of both the dendrite and the spine neck and head. All right, so that's been our presentation on the manual tracing. But I want to encourage you to check out some of these really cool upcoming things that we have here at DR Vision. We've got this Aivia 3D VR contest. So just go to our website, submit your best 3D image data set. We'll render it, we'll model it in Aivia, and we'll send you a free Aivia VR headset viewer so that you can view this reconstruction of your data. Just go to www.drvtechnologies.com/go-to-VR with Aivia to check out this awesome promotion. You'll even be entered into a really cool upcoming contest, so stay tuned for more of those details. We're going on a road trip as well. We might be coming to a city near you. Stay tuned for dates and locations, and we'd love to come visit you and tell you all about the really powerful features in Aivia. And lastly, we have partnered with Interstellate to sponsor your travel with the Neuro Travel Award. We'll release more details by the end of the week, so keep your ears open. Lastly, thank you so much for watching this presentation. I hope it covered everything you want to know about any 2D or 3D neuron analysis applications. I want to give a shout out to the people who have let us use their images. The image credits are listed on our website. Again, that's drvtechnologies.com. So I'd like to take this opportunity to answer any last questions that we might have had during the process. Quinn?
Nope, no questions.
Excellent. All right. Thank you all again for joining us, and I look forward to seeing you guys at our next webinar presentation.